Okay, welcome to the third lesson for my Math 150 class. This we're dealing with graphs and word problems. Today I'm going to go over some trends first of graphs, what can happen. This is going to be a review for most of us. I'm going to introduce maybe some new math terminology and take that in consideration because we're going to use that later on in this lesson. So, what I want to ask is this: if you look at your first three graphs right here, what's the trend? What do they do? Well, we always read left to right. So in this case, this is an increase. So I'm okay if you put this as an increase because it's showing me it's going up. Or you could write it out if you want to. Okay, it's an increase. What about number two? It's a decrease. Now, let's just imagine that is a straight line. This is called, it's a constant. Okay? So, hopefully, number one, we increase our grades. Number two, think about your driving, you're decreasing your gas, and constant, there's a lot of things, consistency, that we might not want to increase or decrease. Maybe you're perfectly fine at how many hours you work during the week or how much an app per hour you make. So that's like a consistent. Okay. The next thing I'm going to kind of show us is this, what we call, it's a U shape. We'll get back to this later on. It's a parabola. Okay. Now, concavity. This means, what does it do? Okay. This means concave up. This means it's going downward, so it's concave down. Okay. So my next four graphs, I want you to look at your U shapes. What are they doing? Okay. Let's take a look at this one. Well, that's kind of going upward. Now, the big thing about this would be, we think it's going downward, but if you think about it, if I take this and put it along here, look what it makes. It makes that U that goes up. So this is concave up, both of them. Now, but the trend is a little different as far as what it's doing. This is increasing. So this is concaving up, it's increasing. This is decreasing. Okay? Now, what about my last two? Well, look at this. This kind of follows the downward. So this means this is increasing because it's going upward. So it's increase concave down. And this is a decrease concave down. Okay, now, I'm going to kind of switch back and forth to our book. I've kind of given us a little short video about how to access the book. So I'm going to go ahead and show you, once you get onto your WebAssign and you click on your book, this is what you can come up with. And we're going to proceed on the exercises 1.3. So if you look at that table of contents, click on 1.3. I'll kind of go back right here and show you. So once you bring this up on your book, go to 1.3 exercises right here. And this is the first example I'm going to do. I want you all to read. Is this an investment? Okay. And I've got several parts of this. Express the original investment in functional notation and give its value. Does it concave up or down? What about when will it reach 55,000? What's the average increase of 2050 and 2060? And finally, which one has the largest average yearly increase between two sets of 10-year or decade span, 2050 to 2060 or 2010 to 2020, and explain your reasoning. Okay, so this is the investment one. So I want you all to think about this. Okay, where does it start at? Well, in this case, let's take a look at it. For functional notation, the year is going to be 2010. And what value do we start with? $5,000. Okay. Now, what's it doing? Well, if you go back to your book real quick right here, look at it. It's kind of going upward like this. Okay. Is it going up or down? Well, it's obviously in this case, it's a concave up. When will it reach 55,000? Well, if I look at 55,000, I go right here. Roughly, it looks like to me it's 2040. The year 2040. Now, at any point during this these exercises, please pause it and go back and forth through your book and listen to the explanations because I may be going a little bit too fast. So please just bear with me, and you can always pause it and repeat these videos as many times as you want. Now, going back to the book right here, what is the average increase from 2050 to 2060? Well, if I look at 2050, it looks like it's roughly at 100,000. And the 2060, if I kind of go way, let me kind of increase that a little bit. Go right up here. I think it's going to be hitting, kind of go over, it's almost splitting it. So I mean, you could say 280 if you want to. I mean, this is just, we're just eyeballing it. So what I'm going to say is, I'm going to say it's going to be 280 minus 105. And I'm going to put it over, how many years are between 2060 and 2050? I'm going to just put it. Okay. So I'm going to put these in parentheses. So what I'm going to do is I'm going to take 280, subtract 105, put it over, in this case it's 10. So you should come up with 17,500. Okay. That's the average that it goes up between 2050 and 2060. That's pretty good. So that means every year roughly it's averaging almost $18,000. Okay, let's look at E. E's asking you, okay, between 2010, 2020, 2050, or 2060. Take a look at that. You want to look at what line, how the line is going and how steep it is. The steeper it is, the more increase it's doing. So I'm going to say between 2050 and 2060. Now, I'm going to look at the same exercises, but part 8 of them. So what I want to do is I'm going to scroll down a little bit more to 8. Okay. It says we're using this graph, this figure, about number of weddings. Okay. What year did it reach the max? That's part A. What is the minimum value? And over what 5-year period does it increase the fastest? Well, let's take a look at the maximum. Well, if you look at it, it looks like to me, when you're looking at all these numbers, it looks like 2.44 is the highest number that I'm seeing. What year is that? Looks to me like it's 1990. Okay. What is the minimum value? That's not the year. Minimum value means what is the smallest number? Well, to me, it looks like it's 1.52. And if you scroll up just a little bit, it's in millions. So we're going to say 1.52 million. And finally, what 5-year period does it increase the fastest? Well, some of them decrease, some of them look straight. I'm looking at between 65 and 1970. Now notice if you subtract them, if you take the 1.8, subtract the 1.52, you're going to get 0.28. That's going to be the highest. Let's see. That's a pretty high value. But if you also look at 2, if I go right here, 45.50, let's see, 45.50, 55.60, 65.70. So between 65, so the 65 is a 1.8, the 70 is a 2.16. That's a little bit higher value than the other one. Even though they're both, take a look at these two right here, they're steeper. So if you subtract those values, you get 0.36. So I'm going to say it's between 1965 and 1970. Okay, now I'm going to skip to 1.4. So I'm going to go back to our book. I'm going to click this right here under chapter 1. This gives my list for chapter 1. I'm going to do 1.4 exercises, and I'm going to use number 4. Okay, Thanksgiving dinner. Now that sounds good to me. I like Thanksgiving. I'm sure most of us do. And so we're going to talk about ovens and preheating. And in this case, if you preheat your oven to 325, it takes roughly 10 minutes. And it wants you to cook the turkey. It's recommended for 15 minutes per pound. So in part A, it's asking you, give me a formula. Give me a good formula. And I want you to use T for total time. And it's wanting you to use P for pound. So that's going to be your 2 letters. Part B is what happens when it's 18 pounds. Well, so time depends on pound. So how I would write this is, okay, time depends on pound. So T of P equals, okay, how many minutes per pound? It's 15. I'm going to put pound in parentheses. But remember, it also takes you 10 minutes to heat up the oven. So regardless of how much turkey you're cooking, it's always going to take you 10 minutes to start up. So what happens when it is 18 pounds? Well, you put 18 in for P, so I'd say 15 times 18 plus 10. So this is going to roughly take you 280 minutes. Or getting close to 5 hours. Okay? My next example I'm going to use, and it's going to be still from 1.4, is number 8. Now, this example this is a world record of a swimming event with 63.2 seconds in 1950. After that, the world record time decreases by 0.4. So that means we're obviously getting a little bit faster. So they're saying each year it decreases 0.4. So here are 3 parts to this problem. Use a formula, um, and you need to choose your units. What using functional notation, what is the world time in 1955, then calculate it. So it means you want to do functional notation, then calculate it. And the last one is, would you expect this to be valued indefinitely? Okay. Now, what I would do is I would say, okay, T, I'm going to say time. So I'm going to just go ahead and I'm going to say T for time. Y is the number, or is the years. Okay. Because it said you start off with 63.2 and you decrease it. So I'm going to subtract it from, it says every year it decreases it by 0.4 Y. So that means every year. Now remember, the key to this is 1950. Because in part B, it's saying, what is the world time in 1955? Well, a common mistake is to say why to use 1955, but that's not it. This is ground zero, okay? This is our initial thing. How many years between 1950 and 1955? What comes out to be 5? So I'm going to say T of 5 equals 63.2 minus 0.4 times 5. Okay? Now this comes out to be, once we calculate this comes out to be 61.2 seconds. Now finally, what does indefinitely mean? That means as the years continue to go and go and go, you know, what happens, you know, as time goes on? Well, it goes down 0.4 seconds. So let's use this year. So we're going to say right now, let's use the year 2020. What's the record? Okay. Well, the difference between 2020 and 1950 is going to be, if you do the math, it's going to be 70 years. So that means it's 63.2 minus 0.4 times 70, 35.2 seconds. Okay? You can use 20, 50, 20, whatever. What it's doing is decreasing. So finally it's going to reach 0 and then do negative. So is it going to be indefinite? No, because at some point it's going to bottom out. And instead of decreasing by 0.4, it may decrease by 0.1 or maybe 0.05. Okay? Now finally, my last example. I'm going to use example number 20. Cattle pen. So I'm going to let you read this. You can pause this and come back. So we got this cattle pen. It's got 400 square foot. He decides to make one of the pens 40 inches long. Draw a picture if needed. What is the length of each side? What's the total amount of fence needed? Well, we know that it's going to be, if the key to this problem is understanding area. Okay? Area is going to be length times width. Well, if we know that the width of is, if we know the length of it is 40, okay? So if we know the length is 40 and the area is 400, that means it's going to be 400 equals 40 for L. What is W? We need to solve for W. So that means we need to divide by 40. In this case, W is 10. Well, you have to be careful because on tests and on homework problems, the width we could say is 10, but it's not, it's asking the width, but what you want to know is what is the perimeter, okay? So perimeter is always going to be 2L plus 2W. So the perimeter of this is going to be 2 times 40 plus 2 times 10, which comes out to be 100. 100 what? 100 feet. Okay? Now, the second part of this, it's saying what would be the total amount needed if it was square? So if it was square, think about this for a second. It means both sides are equal. So A equals, just think of x squared. So we're going to say 400 equals x squared. How do you find x squared? What times what is 400? We'll take the square root. So when you do that, x equals 20 feet. So that means the sides have to be 20 feet because 20 times 20 is 400. Okay, now the third part of this is saying, can two rectangles have the same area but different perimeters? Well, take a look at what we just did. First of all, from our part A, I'm going to kind of put this to the side right over here. So my length was 40, my width was 10, my perimeter in this case we said was 100. Okay, so now let's take a look at when the length is 20 and the width is 20. Okay, well, how many lengths do we have? 2, width's 2, you get 40, add them up 80. So look, you got 80 in for one perimeter, 100 for the other perimeter. So can a rectangle area have the same area but different perimeters? The answer is yes. Okay, finally, what it's asking, this is another one that kind of throws us a little bit off. It says, okay, find the formula if in terms of L instead. Okay, so what we need to do on this one is go back to our original. Area is always going to be, for this rectangle, area is going to be length times width. Okay, but it wants you to have in terms of L. So what I want to do is, if you wanted to substitute these values in and say, okay, what is our square? It's 400 square foot. L is what we're trying to find, but what do we know? Or we need to know is W. So what we need to do is we need to solve for L by dividing by W. So in terms of my length equals 400 over W. So this is what my answer is, but let's take a look at, for instance, a part A. My length was 40 right here. If I say 400 divided by 10, 400 divided by 10 gives me my 40. Or think about when it was 20. 400 divided by the width is 20, it's 20. That gives you all the correct thing. So in terms of L, you have to know W. So when you know W and you plug it in, divide it into 400, that gives you what your length is. Okay, now our assignment is going to be homework 3 on WebAssign. Thank you for listening.